So as Lewis mentioned, and Noah mentioned, right, I joined Dan's lab in I guess it was summer of 1988. And I had gone to Yale thinking I was going to be a whiteboard control theorist. And because I had been a practicing electrical engineer for a couple of years and figured out that was kind of boring. And I wanted to do this control theory stuff. Because I knew how to build certain things. I was an engineer. I had been an MIT undergrad. I had done lots of hands-on stuff, and I wanted to learn to do all this math. And then I got to Yale, and I was talking to faculty members about what I could do and who I could work with. And I met Dan, and Dan explained to me, or beat it into me lately, that I could actually do that kind of math and build things at the same time. And that robotics was actually the way to do that. And that was the thing that actually got me hooked on robotics. And then I had the pleasure of meeting Lewis, Martin, Alon, who just, I can't begin to describe the effect they had on me. And the camaraderie we had in that lab. And then the people who joined the lab and joined the group in the years I was there really made it just a phenomenal learning experience and a great environment to be in. So I thought I'd show a little bit of pictures of some of the systems that I've been fortunate enough to be involved in as a result of my experience with Dan. And it starts with this machine that we built at Yale. It was called the 3D juggler, and this generalized these ideas that Martin had started and Dan had developed about phase regulation and juggling and the like. Unlike Noah, I couldn't juggle then. I can't juggle now. I tried for years in grad school to learn how to juggle, and I just can't do it. But I was pretty proud that I could actually build a machine that juggles. We went from there, and I listened to Dan's advice, and I ended up as a faculty member at Carnegie Mellon. And Dan was fortunate enough or kind enough to involve me in this REX project. And was my group there that put the first visual sensor, a camera on top of REX, and actually started to do some higher level control with a walking robot. We went on to build these climbing robots, which was a collaboration cross-country, a huge number of universities and professional groups, including myself at Carnegie Mellon at the time, and people at Boston Dynamics and people at Michigan. And that's about the time Dan moved to Penn originally. And so it involved a bunch of people here. About halfway through that project, I moved to Boston Dynamics, where I've been ever since. And the machines on the bottom are just a smattering of the machines that we've worked on there, all influenced by these ideas of paying attention to the feedback, figuring out how to sequence programming, sequence behavior, and regulate phase. All of these machines have phase regulation problems baked into them. Let's see if we can watch some videos. This is the original 3D juggler. This was back in the Yale lab. And this is, I think, one of the first machines that we got any real publicity for. I think Annie found the New Haven Register article that cited us, has a lovely picture of me posed by some photographer leaning on the robot. But this was the first time we had one of those phase regulation machines. And let me tell you, a black robot in a black room with a white ping pong ball is wonderful photographic material. But as Noah pointed out, the real thing Dan taught me, or Dan and I learned about through doing this project, was how to solve these phase regulation problems. And at the time, we were watching work that was coming out of Raybert's lab at MIT and totally enamored at the ideas of working on, walking or hopping machines, but we were stuck with juggling. And I think we found a bunch of really interesting problems in that space that turn out to be very much related. And then, as Noah pointed out, the culmination of this, I think, was some of the work that showed up in Rob Burge's thesis. And this is video from his thesis on these ideas of sequential composition, how to take lots of simple behaviors and sequence them together in a smart way, in a way that's principled in order to produce more complicated behavior. So that's the moral equivalent of Noah catching his juggling bag on the back of his neck, only done by a machine. The machine, of course, well, it doesn't have human brains and doesn't have hands, so it can squeeze the ball, can't hold the ball to control things. So how did we build these things? Well, I think I spent probably a third or a half of my career as a graduate student, not actually working on robotics, but working on computer architectures and programming models to make these things work, right? This is 1990 plus or minus. And we're trying to build this machine that has a vision system, has some, computer smarts in it, has a high performance control system. Lewis described, that part of his thesis, which was focused on model-based adaptive control for the robot. Well, Lewis's thesis actually lived in the middle here, right? So all of this stuff was actually stuff Lewis had built. The robot we used for juggling was one of the robots he used for his experimental work. And I do have lovely memories of large dumbbell-sized weights flying towards various researchers sitting behind the protective glass in our lab. But we had to build a vision system. We had to do all this stuff. And my predecessors, Martin and Lewis, had started to work with a professional engineer on these computer systems, these things called transputers, that were going to revolutionize parallel computing. I think they still do, sort of, but they were a commercial flop. Nonetheless, I still have a paperweight in my office, which is one of the, I think I had 17 or 20 of these things all plugged together in a 19-inch rack, a little bit of duct tape, some loose wires everywhere, lots of wire wrap. But I'm very pleased to still have one of those. Lewis, you'll be happy to know one of the people that you inflicted the transputers on at Woods Hole actually works for Boston Dynamics now. And he occasionally pokes me about them. Nonetheless, this was fun. We made a lot of progress. I think we learned a lot. And I think this is Dan's first appearance in Science, which is in the bottom of this slide, which was a little blurb in their news section. I think it was 1991 that they actually took note and thought this was kind of interesting. And I guess I'm going to call this the beginning of science robotics actually starting. Nonetheless, we went on, right? Rex got created. I wasn't actually part of that, but I was fortunate enough to get involved with sort of how we did higher level control on Rex. And so computing evolved. We went from all of these transputers plugged together in wacky networks to PC 104 computers plugged together in wacky networks with more wire wrap bits holding them together. Now we're adding, an integrated camera, which was only about this big, quite cell phone sized yet, onto the robot. And we're actually starting to do some higher level control on these machines. The same ideas all permeate this. It's all about phase regulation and paying attention to the dynamics and the interplay of the dynamics with the sensing. And we were able to produce, these behaviors that basically made the robot easier to drive, whether it was through automated visual guidance of the robot or driver assist kind of features. And, at the core, there was some fundamental science that drove that. Those ideas progressed. We got to the point of actually having, again, this very large collaborative DARPA-funded project focused on climbing robots, still with legs. The idea being, can you build machines that actually climb sort of arbitrary surfaces using base technology? At the very, very beginning, that's the robot climbing on like a styrofoam wall, inclined at about 60 degrees, and it took one of my grad students holding it carefully to get it to actually successfully take a step. Nonetheless, about 6 or 9 months later, we actually had the robot climbing these vertical, easy to grip surfaces and being drivable. So here's somebody actually watching the robot and steering it and giving it relatively high level commands, but the robot's doing all of the details internally to figure out sort of how to move the feet. Actually, this was the start of Clark Haynes's thesis work that we'll see shortly. In the end, after a lot of work on the control and the behavior of the robot, automating how the robot actually sequences all of its foot motions, and a huge amount of progress on the mechanical design of the robot itself, thanks to our collaborators. in the biomechanics world, in the mechanical design world, both academically and the group at Boston Dynamics, we finally got to a machine we literally stuck on the side of a stucco building and said, go. And I think it took about 15 minutes. Our test supervisors, the people at Southwest Research Institute, had laid out a large tarp at the base of where the robot was climbing because they were convinced we were going to fall off the building and they wanted to catch all the parts so they could take pictures of them. So they were very, very sad when the robot actually succeeded and got to the top of the building. No idea how I'm doing for time here. Oh, we're not. So that brings us to about 2006. And much to Dan's chagrin, this is when I decided to leave academia and moved from Carnegie Mellon to Boston Dynamics. And Dan gave me many, many lectures on how this was a horrible disservice I was doing to the world. And I believed him for the most part. But I was convinced that I could be more productive. I think maybe about 3 years ago, Dan might have said it wasn't a bad thing that I had moved. And for me, I think it was a thing that I learned very early on working in Dan's lab and working with this very close community of graduate students and faculty that had formed around doing robotics at Yale, that the power of research came from the collaboration. And it came from working across disciplines and listening to different people. And that was one of the things that had drawn me to Carnegie Mellon initially, because, hey, there are lots of people doing robotics research, and I made great friends and great collaborators while I was there. But we just couldn't quite do things at a scale that was really satisfying for me. And so, so I've been at Boston Dynamics for the past 16 years. And, these are just some videos. Oops, I wasn't supposed to play that way. Oh well, we'll let that play that way. I walked in the door at Boston Dynamics, and the first thing I had to do was ship these little dog robots off to academic partners. I had actually written half of the proposal at Carnegie Mellon before I left. All of a sudden, I was the equipment provider back to Carnegie Mellon and 7 other groups around the country, including a group at Penn. And my responsibility here was to, in 3 months, design and ship the interface that everybody was going to use for these robots. And that was very much, again, influenced by these ideas that I had learned about what does it mean to actually program a robot. We went on to do things like build, this was a robot we called Wildcat or Cheetah, which was, very fast running robot that could run across a parking lot at 20 miles an hour. I will never turn the audio on for these videos because the machine was literally about 120 decibels. Everybody if you see any people in any of these videos, you'll see them wearing big racing radio sets so that we could actually talk to each other. But this was the stuff that was totally motivated by the juggling work. Right? It is all the phase regulation problems Noah talked about. It is all these ideas about programming work. Plus, it's combined with all this other cool stuff I had started to learn as a grad student and then continued to learn about these non-holonomic systems, right? This is a momentum-constrained system. It's rarely in contact with the ground, and it needs to do the right things both while it's in contact with the ground and while it's flying through the air, in order to maintain its balance and keep itself well-oriented. Here, I'll play this one full screen the way it is, because I think it's the ultimate example of that. This is not a fancy legged robot. It's not a juggling machine, right? This is a robot we called Sandflea. And it's a little 4-wheel differentially driven car that you can drive around. Well, it's got one really big trick that most little differential drive carts don't have. And that's when it actually comes up to an obstacle, rather than trying to climb over it, it can actually hop over it. So it points itself up and then it flies. Now, that time you'll notice it landed on its wheels, right? Watch this one. actually goes up and it starts to turn over backwards and it stops. Now, somebody taught me some physics, and things that fly aren't supposed to do that, right? Well, what were we doing? We were actually using the wheels of the vehicle as control moment gyros to control its attitude in flight. So the drive system of the robot is designed, both to let it drive around, plus spin things fast enough that it can actually absorb momentum in flight. So you combine that with a super smart mechanical engineer who did design work on the wheels so that they could absorb all this landing shock. And suddenly you have this thing that you can literally launch 10 meters through the air, have it land and bounce not more than about half a meter from where it struck the ground, because you combined the sensing with the control system and the smart design to get that all to work. Where does that take you? Well, if you paid any attention to what we've been doing at Boston Dynamics in the last couple of years, we're building spot robots. This is, our first cut at a truly commercial, useful quadruped. Personally, I've been working mostly for the last probably about two and a half years on our manipulation efforts. So how do we combine manipulation with all this locomotion work that we've done? This video gives you a quick overview of some of that. So here's 3 spot robots acting in coordination, not juggling, jumping rope, similar. But more interestingly, a robot with an arm autonomously picking up the trash, right? I'm cheating a little bit when I say fully autonomously. There's a user who's saying, there's a thing there and a thing there and a thing there, go pick them up. But that same machine can go drag cinder blocks across the hall. It can do exciting chalk drawings on the pavement, right? And it really is becoming, I think, one of the first functional legged mobile manipulators that's available in the world. And I'm super excited about that. But what do I get from all of this experience? Well, when I started working with Dan, robots were a bit of a fantasy, right? I think thanks to some of the groundwork he's laid, some of the work the people in this room have done, others have done, I think robots actually can work in the real world these days and do useful things, and not just not menial tasks. They can do real tasks. Feedback and composition of feedback really helps with programming those systems. If you followed what we did at Boston Dynamics, there were the earlier walking robots, Big Dog, LS3. Those machines were very hand programmed. It took a team of a lot of people to keep them running and keep them balancing. When we transitioned to Spot, I was fortunate enough to be able to tell the people who were holding the purse strings, no, we're going to wait 6 months and not have a demo for a little while. And we completely re-architected the underlying balance control systems using a lot of these ideas that I started to learn about when I was a grad student. And the result is we got a system that was suddenly much more robust, much more scalable, much easier to maintain. And I think that plays a key role in what we're doing. The sad thing is that once you add the arm to them and you go ask them to do real tasks, they're still hard to program, right? This is a picture of us, in our lab doing an automotive inspection task with a robot. And we're going to try and deploy this as a solution for a customer in the next couple of months. And there's still a lot of handwork that has to go into those systems. And I'm eager for us to figure out how to eliminate that. And this is probably the best bit of legacy that I can offer for Dan for what he's done. My group at Boston Dynamics does an annual superlatives event, and we nominate each other for great things, interesting things we say, memorable features of what we've done. And I got this year most likely to tell you to remember the off-diagonal terms. And I think that really goes to one of the things I learned from Dan a long time ago, and that is to pay attention to the whole system, that it's not as simple as just picking out the one interesting or hard piece and working on that. pay attention to the whole thing. And I hope he's imbued all of you with that. I really appreciate it. And can't begin to thank him enough for the influence he's had on my life and my career. Thank you.